All right, everybody. I know the notes say we're going to do this on review day, but I think we can do it now. So let's just do this. I can't emphasize this enough. This is in our notes from last day. Anytime you do acid-base problems, we need to know, is an acid protonated or deprotonated? And it's all about pH, right? So if the pH of the environment is above a pKa for an acid, pKa for an acid, I'm trying to highlight the A here. Okay. Somebody's trying to tell me something. We're not going to get a lowercase subscripted A there. If the pH is above the pKa, think about it. Think about it. Don't memorize. Memorizing is just dangerous. pH above, that means high pH, right? Is that basic or acidic? High pH is basic. Oh, does that mean there's protons around, or does basic mean you're going to take protons away? You're going to take protons away. So high pH, a proton will be missing its proton. An acid will be missing its proton. What I'm trying to say is the acid will be its conjugate base. pH below pKa. So if the environment has a low pH compared to pKa, low pH means acidic, right? The acid will be protonated, means the acid is an acid. Okay, in this problem, we're starting with everything protonated. Do you know how I know? Everything's at pH 1. On my handout here, there's not a single pKa that's listed anywhere here with a number less than 1. Means every proton is in an environment where every acid is in an environment where it will have its proton. So what would alanine look like at pH 1? It would not look like this. 1 is below 9.87. Yes. So this would look like this, the acid form. 1 is below 2.35. It will not look like this. This is the base form. It will have its H. It will be a carboxylic acid. Okay. So acid form, if you're below the number. So this page is all at pH equals 7. So that's why this is an O- on this page. 7 is above 2.35. 7 is more basic than 2.35. 7 removes a proton from an acid that used to have a pKa of 2.35. The environment makes this look like this on this page. But on our next one, where we're doing our problem, and here it is, we have to draw isoleucine at pH 1, and it has an amide to histidine and arginine. Isoleucine, histidine, arginine. Can we remember those things so we can find those groups and use them over here? Isoleucine has a sec-butyl group. Here's where students who have gone through Henry Ford have a slight advantage of other students. Your teachers in biochemistry will make you memorize all these amino acids, and you'll say, oh yeah, isoleucine's the one with a sec-butyl and leucine's the one with an isobutyl. But you don't have to do that for me. You got it right here. So I'm going to remember sec-butyl. What was the other two? I can't remember. Histidine. Histidine has CH2 imidazole, and it goes C-double-C towards the NH in the imidazole. And then I can't remember the other one. Was it arginine? I think it might have been. Where were we? We were over here. Arg. And arginine has CH2 3 times, then a guanidine. See, I can do that from my memory now. I have the words for it. Of course, I've been doing it a long time. That helps a lot. So isoleucine has a sec-butyl group. Amino terminal. Why amino terminal? Because it's the one listed first. Why is it protonated? Because we're at pH 1. Everything has to be protonated. Carbonyl, sec-boo. And next one, NH. I can keep going down here. CH2 goes to a C in the ring. CCC went to an NH. Imidazole. Double bond to N here. Close the ring. And what about Arg? Arg in black. Why is this going to be OH? Well, at pH 1, a carboxylic acid will be protonated. Arg is CH2 3 times. 1, 2, 3, NH, guanidine. Protonated for sure. Stays protonated. Oh, wow. You're so harsh. There's a plus there. Okay. I really don't like the plus looking like that. Bothering me. Nice. All right, now what am I going to try to do? I'm going to try to do some weird stuff. I don't want, I know, on a test you have to copy paste millions of times. But I think it would be best for us to be able to move on if I do copy paste. No matter what I do, I'm not fitting that sucker in the box. Okay, so I'm going to add 1 mole of NaOH to 1 mole of this. Which H comes off first? Well, whoa, we didn't finish. 1 is below 6.1. Why did I say that? Histidine. Histidine right here. H-I-J-K. It says 6.1 over here because if the pH is not 7, but it's 1, 1 is below 6.1, this needs to be protonated. So it'd be NH plus. Yeah. So, yeah, we gotta be careful. Sometimes the side chains get protonated. So we're going to have an NH plus there in both of these. And I don't know why I decided to put that in the ring. There we go. And all the numbers, I'm going to put the numbers in black. We have a 6.1 here. I got to write it there. I need the isoleucine ammonium number. And I need the guanidine. That one I happen to have memorized. It's 12 point. Yeah, I don't have it memorized. Isoleucine ammonium number and arginine carboxylic number and side chain number. Isoleucine 9 point. I'm going to go 1 decimal as you should on the exams too. 9.8. And then arginine, I need 2 numbers. 2.0. It was 12.5. Okay. I'm forgetting already. Isoleucine was 2.0. Which one was it? This one? 9.8. Totally forgot. 9.8. We need these numbers because if we're not taking the right H's off at the right time, 12.5. And I can't remember. What was it? Arg, carboxylic acid on the right side, 2.0. Which one's coming off first, ladies and gentlemen? a 2, a 12.5, a 6.1, or a 9.8? Answer 2. Eraser. Take it off. Put an O- in its place. Problem is all of these are missing the... That's kind of cool. So this one's also missing that. What's the next one that comes off after 2.0? Is it not the old 6.1? Oh, lucky, lucky. 6.1 is done. It's off. Did I put this in the right box? No. Can I do that? Doubt it. I got cocky there. I was in the wrong box. Well, please. Put it in the right box. Ish. Take that O off, that H off. The 6.1's already off. What's the next one to come off after the 6.1? The 9.8. I don't know why it's not remembering what I pasted before. There we go. All right. So 9.8 is going to be off. Carboxyl's off. NH2, neutral now. And the only thing left is our 12.5, the most weak acid. I'm just going to move that number closer to where it belongs. Last thing to come off. That's a good spot. It's going to be an NH2. It's going to be CO2 minus. It's going to be NH neutral. And I believe that's the end of the acid base portion of this question. Two. And now the question is, what does acetic anhydride do? Well, this is just kind of a review. It's going to acylate all amines. Acylate all amines. If there was alcohols, it would happen too. Pretty close. Aliphatic amines. So in our example, we really don't have, well, yeah, we have one over here. Aliphatic just means not attached to anything special, not in an aromatic ring. You could argue an anhydride would be made. Carboxylates. I don't think I'm going to put this question on your test. If you want to see the answer, though, C key. There you go. And we'll finish this segment up by talking about why is this PI stuff important? And wait, we didn't even do the PI. PI Wednesday. But right now, if you remember, I stands for isoelectronic. Then we need to find the version of all of these where the molecule has a net charge of 0. It's called the isoelectronic point PI. So I'll put the charges in pink. overall charge of the molecule on the top of the screen was +2. It had 2 ammonium ions. We got rid of one of the pluses. Sorry, we got a minus to cancel one of the pluses here. So overall plus plus minus is now, are you surprised the charge is going up? Or sorry, down +1, up. It's getting more negative each time. Here we have 2 pluses and a negative. Is this the same as, oh, wait. I didn't even start in the right spot. +1, +2, +3. You're being so polite today. Thank you. +1, +2, +3. And then +2. And then we have a plus canceled by a minus, but this one's not canceled, so +1. So the isoelectronic molecule that we want for PI is there. And at the end, it became -1. It's got a minus. So we need to make sure what happened here stays happened. I don't know if I worded that properly. What did happen there? We took this proton off. So this is the molecule, the PI molecule right here. I need color that stands out. So I want to keep off the 9.8. That's the last one that came off to make this neutral. And what's going on here? I need this thing needs to stay on. I can't, so keep on the 12.5. So you look on either side of the PI molecule. And once again, I think the video does a nicer job than what I just did here. Because I need it to look like this. I don't need it to look like this. That's not a 0 molecule. That's not a 0 molecule. I need it to look like this. So make sure this one stays off. How do you keep an H off? Do you go above that number or get below it? If you go above the number, the H comes off. If you stay below a number, the H stays on. So if I'm below 12.5, this stays here. If I'm above 9.8, this stays off. Okay, so PI is 12.5. Notice there's a lot of numbers at the start of this question, but only 2 of them are ever relevant for PI. 12.5, 9.8 over 2 means you'll have as many of these with the H. I'm going to have a number lower than this one. So I'm going to have as many of these protonated as I have these deprotonated. That's what I want. And that's 22.3 over 2. No calculators. 11.2 with rounding. 11.15 goes to 11.2. So that's the PI of that tripeptide. Read about PIs. And PI, we'll put it down here too. We already worked on that one. We can quickly do asp-arg and asp-seer just by looking at the original handout. PI of asp. Asp is here. Right now, this molecule has a negative charge overall. -1, -1, +1. That's -1. I need to get it to be 0. So what's going to happen? I got to protonate one of those 2 minuses to make it neutral. Which one protonates first? pKb of 14 minus 3.9 or 14 minus 2.1? Well, 14 minus 3.9 is a lower number. That's better. So I need to get this thing to have a proton. I need to get below this number. But I do not want to get above, below 2.1. I need to stay above it. There's your numbers. 2.1, 3.9 over 2. 2.1, 3.9 over 2. 3.0 exactly. Arg. Similar story, but with different charges. You ready? Arg. Right now it's +1. So I need one of these guys to come off. Which one's coming off first? The more acidic one or the less acidic one? I answered my own question. I gotta get that off. I need to be above 9.0, but I need to stay below 12.5. I don't want this one off as well. Notice I'm ignoring 2.0. Doesn't matter about that one. I need to get above this to take it off and stay below this to keep it on. And then one of them will be neutralized and this will be plus and minus 0. 9.0, 12.5, 2. 9.0, 12.5 over 2. I forgot they had divided by. It's 21.5 over 2 is 10.6 with rounding. Is that right? You can always check your work. 10.6 is only 0.4 from this, and it's 0.9 from this. That's a bad answer. 1.9 from that. What did I say? 21.5 over 2. 10, 21. I'm going to write it down if it lets me. Half of 1.5 is 0.75. Half of 20 is 10. 10.8 with rounding. 11.8. No, 10.8. It's 21.6. Now it works. Got it. Asp's here. Tough stuff. It's a dipeptide. Asp is connected to SEER. Asp is here. This is no longer this. It's an amide with SEER. This is no longer an ammonium with a pKa. It's an amide. So ignore that. The picture in your mind is between these two. And it's going to have a carboxyl over here. And it's going to have a carboxylate over here. And an ammonium over here. I need to get this thing to be protonated and keep this thing deprotonated. Once again, do that on your own because I just went through a whole bunch of stuff. The two numbers I care about are 3.86 and 2.21. 3.9, 2.2. 3.9, 2.2. 3.9, 2.2. And with rounding, I think you're going to get 3.1. 6.1 over 2 is 3.05, rounds to 3.1. It's good. Okay. So diagram the electrophoresis experiment for the separation. I erased some stuff there. We don't even know what electrophoresis is yet, do we? Electrophoresis experiment. Well, as it suggests, you're using electricity and you're separating things based on two things really: charge, which is all PI is about, charge, and size. Size we're going to ignore in our discussion, but we have things like acrylamide gel that are used during this experiment, which can sort things according to size and charge. And what happens is, quite simply, we can actually do the lecture with the problem here. You need 2 electrodes. Positive electrode is the one that's going to accept electrons, so where oxidation is going to happen. So we call that the anode. Anode, the only real definition for normal electrical chemistry. Anode is the site of oxidation. Notice I didn't use the charge in the definition. Cathode is the site of reduction. That's the only definition of cathode for normal electrochemical experiments. And ideally, you want to separate these so they're spread out as much as possible in between the two electrodes. So what would be a nice pH to separate these things as nicely as possible? Well, what are our extremes? 11.2 is the high and the low is 3.0. So what's half of 14? 7. We'll make it 7.1 to make it interesting. So step 1, buffer to pH 7.1. Median or average pH. Okay then. So now the question is 7.1 above or below 3.0? And it's well above. Do you know what that means? The environment is more basic than this molecule. It's going to take a proton off. If the environment has a higher pH than the PI, just like we said with these two sentences on our previous page. Oh, that was on that page. I just saw it. If pH is above pKa, right, it's going to be deprotonated. Hey, what happens to something's charge when you deprotonate it? Does it get more negative or more positive? Well, remember, a proton is positive. If something's protonated, it's going to be more positive. If it's deprotonated, it's going to be more negative. So we're going to be above this number. We're going to be more negative. We're going to be 4.1 units above this number because we chose 7.1. So that's a big gap, right? So 4 units above 7. And asp, you took away a proton, it became negative, it's going to go towards the left. So we are going to say that asp will form a band right here. In that band, we're going to have ASP. Now, right close to it, but not quite as negative, is the dipeptide asp sear. And these experiments are sensitive enough that if the difference is anything, even 0.1, you can separate things. And there you go. You got asp sear right there in that band. And then 10.8 is where's the middle of our experiment here? We have a nice gray. We never use gray for anything, but the middle's about right there. And we're going to be about the same. Let's see, the difference between 3.1 and 7.1 is 4. Difference between 10.8 and 7.1 is 3.7. So not quite this distance on the other side will be the arg. Not quite as far as the asp sear because it's closer to 7.1. And that will be the arg. And this is 4.1 away. So that'll be further away than the asp was by just a hair. Will be the tripeptide isoleucine histine arginine. And we're going to put it way over there in baby blue. a little further than asp was. And that's isoleucine, his, arch. And what you do after this experiment's over, you take one of those blue lights and you shine it over the chamber, and you'd see an actual streak here, and you'd cut it out with a knife. Seriously, you'd cut it out with a knife, put it in a beaker, dissolve away the acrylamide using a solvent, and evaporate the solvent after filtering and all the good stuff. You get asp by itself, and then same for this fragment here. You get asp sear, and it's a nice way to purify things and a nice way to end our segment. And we'll pick it up after this. See you soon.